Alright, cool. So I'm gonna do the first problem, and I'm gonna do my best to try to explain it. It's kind of complicated. Okay, so in the problem, it tells you that there is an object, which is a box, that's on a surface with zero point 0.5 newtons of friction. Okay, and it tells you that it's being pulled, and yeah, so that's pretty much all it tells you. So the first thing that I tried to do was that I tried to find the weight. Okay, and what I did was I knew the equation weight equals net force times mass. So you just set it up 10 newtons over 1 kilogram times the mass, which is given in the problem, which is 20 kilograms. You cross it out, and then you get weight equals 200 newtons. So you know the weight now. Alright, so we have the weight now, so we can find the normal force automatically because we know that normal force equals weight, and we know that the weight is 200 newtons. So that's pretty much given. Alright, and that's pretty much all that you can solve in problem 1. Actually, I want to explain a little bit of
great customer service, great patient care.
I kind of want to explain the diagram that I drew. So what I did was, you just put the gravities acting down upon the object, and then you circle the object, which is the box up there, and then, the floor is pushing up on it because it's an interaction. You draw the friction towards the left, because that's pulling back on the object, stopping it from moving, and you put the force of the man pulling or whoever's pulling it to the right. Okay, and that's pretty much it. You do the vector sum diagram, and then you see that it's equal to 0 because it has no acceleration. And so yeah, that's pretty much it. I just wanted to finish off the problem. Okay, so now we go to the second problem, right? And the second problem, they change it up on you a little bit. They don't make it a constant velocity. They make it that the box is accelerating 2 meters per second every second. Okay, and this is pretty much what it does is messes up your vector sum diagram, because when you put them up head to tail, they don't add up to 0 anymore because it's accelerating. It's not constant. Okay, so the first thing that I did was that I drew the vector sum diagram, and it changed it up a little bit. What happened was that you make the arrow with the force of the person pulling it longer than the friction, because accelerating is not constant, it's not equal 0. And because it's longer, you have to make the appropriate corrections to the vector sum diagram. So what you do is you do the head to tail thing again, and you make them not equal anymore, because the friction and the force of the object of the person being pulling, that made no sense. I'll try to say it again. Okay. The length of the vector sum diagram for the portion of friction is shorter now than it is for the force of whatever's being pulled or whoever's pulling it, right? So you do the appropriate vector sum diagram, and you can see that it's disproportional. Okay, so now we realize that it's not equal to 0 anymore. The net force isn't equal to 0. So you try to do your best to find out what we can solve, right? And we already found the weight of the last problem. The weight doesn't change. It's the same object. But you can find the friction now, because the friction has changed because the object accelerating, right? So today in class we learned this really cool formula. It was friction equals something, this weird m thing. I forgot what it's called. I'll Google it later. I'm too tired. And then times this n thing, which I'm assuming is like weight, right? And this m is probably the friction, which was 0.5 newtons times 200 newtons. Right, and it gives you the amount, or the amount of friction, or the force. Okay, how can I say this? Okay, let me think about it. Give me a second. Okay, so I thought about it, and this number that you get when you do this equation gives you the amount of friction that acts upon the object. I remember this because in class, I think it said that like the heavier the object, the harder it's to pull. When there's like more friction or something, it's got to do with the weight. So I guess this is what I thought. This is how I thought about it. It was just the amount of whatever that it takes to act upon the object. Okay, so now you have the number or the value for friction that's acting upon the object we're trying to find, which is the box. So what I did was you just plug it in. And you know that friction is the arrow right here, and friction, I drew it down here. Okay, so in order to complete the vector sum diagram, we need to find the net force. So what I did was I put it into the equation, which was net force equals mass times acceleration, right? And then you don't know the mass, you know the weight from what you did over here, so you need to convert um, this value, which is in newtons, to kilograms, which is an actual mass, right? So you do that. You just 200 newtons. Um, you could put up here, right, into the 10 newton category, and then you divide it by 10 pretty much. So you just get the 200 kilograms. All right, and then you get the 200 kilograms, and you multiply that by the acceleration rate, which is 2 meters per second squared, right? And then in class today, we talked about how kilograms times meters per second square is pretty much Newton, right? So you just multiply 20 times 2, you get 40 newtons, or in the case, you get 40 kilograms times meters per second squared, which is just 40 newtons, right? And then you put this on the side over here, right? So in class today, what we did, we just kind of added them up. So we knew the 100 newtons, which was the force of the friction that was acting upon the object. We have the net force now, so you just kind of add them up. 100 plus 40 newtons is 140 newtons, right? And that, because it's a vector sum diagram and the bottom side has to be equal to the top side, you know that this now is equal, it's balanced, you know the net force. So you know that the top, which was the force of the person that was pulling it, is equal to 140 as well. Okay? And you can also find the two side ones. You didn't know what the amount of force was that the floor was pushing up on the object, but you knew that the weight was 200 newtons, right? So you just plug that in right there. And then because it's an interaction, they both act upon each other the same way. Because this side equals 200 newtons, this side also equals 200 newtons. Okay, so I'm done. Hopefully that wasn't too confusing. It made sense in my head. And yeah, sorry about the sloppiness, I guess. Alright, I'm done. Thank you.